Road to Olympiad.
Welcome to RTO. Consider the following problem. Find all non-negative integer solutions a, b, c, and d such that 2 to the power of a times 3 to the power of b minus 5 to the power of c times 7 to the power of d is equal to 1. Since we have plenty of power of prime numbers here, we are most likely going to play around with the divisibility of prime numbers. There may be quite a lot of possibility to check out, but in the process of analyzing, we will find out that there are a lot of similarities in the steps and we can eliminate a lot of possibility throughout the process. Pause the video if you like to give this problem a try, and when you are ready, keep watching to learn how to solve it. To solve this problem, we start by noticing that there is only one even number in the equations, which is 2. So, by rearranging the equation into 2 to the power of a times 3 to the power of b is equal to 5 to the power of c times 7 to the power of d plus 1, we notice that the right hand side is the sum of two odd numbers, and thus they must be even. This implies that a must be at least 1. Now, consider the case if b is equal to 0. In these situations, we have 2 to the power of a minus 5 to the power of c times 7 to the power of d is equal to 1. If c is non-zero, we have 5 to the power of c times 7 to the power of d is a multiple of 5. So by taking congruent modulo 5, we have 2 to the power of a is equal to 1 mod 5. We can easily check through the pattern of the power of 2 that we must have a is a multiple of 4. With this, 2 to the power of a will be equal to 1 mod 3. And this implies that 2 to the power of a minus 1 is a multiple of 3. However, from the equations, we have 2 to the power of a minus 1 is equal to 5 to the power of c times 7 to the power of d, where the right hand side have no factor 3. Therefore, we reach a contradiction, and thus there's no solutions for c is non-zero. What if c is equal to 0? We will then have 2 to the power of a minus 7 to the power of d is equal to 1. We can do some direct computation to find out that for a is equal to 1, 2, and 3, we only have two solutions for a and d, which are 1, 0 and 3, 1 respectively. And for a is at least 4, we have 2 to the power of a is a multiple of 16. So by taking congruent modulo 16, we have negative 7 to the power of d is equal to 1 mod 16, or simply 7 to the power of d is equal to negative 1 mod 16. Checking through the power of 7, here we have no solutions for d. Therefore, in this case, we have two solutions, namely 1, 0, 0, 0 and 3, 0, 0, 1. For the second case, we have b is positive and a is equal to 1. Here, we have 2 times 3 to the power of b minus 5 to the power of c times 7 to the power of d is equal to 1. Since b is positive, 2 times 3 to the power of b is a multiple of 3. So, by taking congruent modulo 3, we have negative 5 to the power of c times 7 to the power of d is equal to 1 mod 3, which is simply equivalent to 5 to the power of c times 7 to the power of d is equal to negative 1 mod 3. Notice that 5 is equal to negative 1 mod 3 and 7 is simply 1 mod 3. We can simplify the equation into negative 1 to the power of c is equal to negative 1 mod 3, which clearly gives us that c is an odd number. Knowing that c is odd, 5 to the power of c times 7 to the power of d must be a multiple of 5. Therefore, by taking congruent modulo 5, 2 times 3 to the power of b is equal to 1 mod 5. which can be simplified into 3 to the power of b is equal to 3 mod 5. Checking through the power of b again, we have b is equal to 1 mod 4. Now, if d is not equal to 0, 5 to the power of c times 7 to the power of d is a multiple of 7. So by taking congruent modulo 7, we have 2 times 3 to the power of b is equal to 1 mod 7. Simplifying this gives us 3 to the power of b is equal to 4 mod 7, which yields the solutions b is equal to 4 mod 6. However, this is impossible because b is equal to 1 mod 4 tells us that b is an odd number, whereas b is equal to 4 mod 6 implies that b must be an even number, which is a contradiction. So there's no solutions if d is not equal to 0. So what about d is equal to 0? We'll have 2 times 3 to the power of b minus 5 to the power of c is equal to 1. Clearly, if b is equal to 1, we have c is also equal to 1. If b is at least 2, then 2 times 3 to the power of b is a multiple of 9. So taking congruent modulo 9 gives us negative 5 to the power of c is equal to 1 mod 9. Or 5 to the power of c is equal to negative 1 mod 9. Checking through the power of 5, we have c is equal to 3 mod 6. Here, we can argue in a similar way as in case 1, where from c is equal to 3 mod 6, we have 5 to the power of c is equal to negative 1 mod 7, which implies that 5 to the power of c plus 1 is a multiple of 7. However, from the equations, we have 2 times 3 to the power of b is equal to 5 to the power of c plus 1, where the left hand side has no factor 7. Thus, this is a contradiction and there's no solution if b is at least 2. Therefore, the only solutions in this case is 1, 1, 1, 0. Moving on to the last case, we have b is positive and a is at least 2. Since b is positive, we can take congruent modulo 3 to get this, and since a is at least 2, we can take congruent modulo 4 to get this. Where the first equation is simply 5 to the power of c times 7 to the power of d is equal to negative 1 mod 3. Since 5 is equal to negative 1 mod 3 and 7 is equal to 1 mod 3, this can be simplified into negative 1 to the power of c is equal to negative 1 mod 3. Similarly, the second equation is simply 5 to the power of c times 7 to the power of d is equal to negative 1 mod 4. And since 5 is equal to 1 mod 4 and 7 is equal to negative 1 mod 4, we can simplify the equation into negative 1 to the power of d is equal to negative 1 mod 4. Both equations tell us that both c and d must be an odd number. And thus, we can have 5 to the power of c is equal to 5 mod 8 and 7 to the power of d is equal to 7 mod 8. Now, 2 to the power of a times 3 to the power of b is equal to 5 to the power of c times 7 to the power of d plus 1. Under congruent modulo 8, this is simply equal to 5 times 7 plus 1, which is 35 plus 1 mod 8. Or 36 mod 8, which is equal to 4 mod 8. This tells us that 2 to the power of a times 3 to the power of b must be a multiple of 4, and is not a multiple of 8. Therefore, a is equal to 2. Knowing that a is equal to 2, we now have 4 times 3 to the power of b minus 5 to the power of c times 7 to the power of d is equal to 1. Remember that c and d are both odd numbers. Taking congruent modulo 5 and 7 here, we have 4 times 3 to the power of b is equal to 1 mod 5, and 4 times 3 to the power of b is equal to 1 mod 7 respectively. The first equation can be simplified into 3 to the power of b is equal to negative 1 mod 5, and this gives us b is equal to 2 mod 4. The second equation instead can simplify into 3 to the power of b is equal to 2 mod 7, which simplify into b is equal to 2 mod 6. Solving these two equations, we have b is equal to 2 mod 12. Putting all this information together, we can let b is equal to 12k plus 2, where k is some integers. We have 5 to the power of c times 7 to the power of d is equal to 4 times 3 to the power of 12k plus 2 minus 1, where the right hand side can be factorized by using the difference between 2 square formula into 2 times 3 to the power of 6k plus 1 minus 1 times 2 times 3 to the power of 6k plus 1 plus 1. Notice that 2 times 3 to the power of 6k plus 1 plus 1 can be written as 6 times 3 to the power of 6k plus 1, or 6 times 9 to the power of 3k plus 1, and this is simply equal to 6 times 2 to the power of 3k plus 1 mod 7, because 9 is equal to 2 mod 7. Notice that 2 to the power of 3 is equal to 8, which is 1 mod 7. We can further simplify this into 6 times 1 plus 1 mod 7, which is equal to 0 mod 7. This implies that 2 times 3 to the power of 6k plus 1 must be a multiple of 7. Now, notice that both 2 times 3 to the power of 6k plus 1 and 2 times 3 to the power of 6k plus 1 minus 1 are both odd number and has no common factor other than 1. And since 2 times 3 to the power of 6k plus 1 is a multiple of 7, this implies that the other counterpart, which is 2 times 3 to the power of 6k plus 1 minus 1, must be a multiple of 5 then. In fact, we have 2 times 3 to the power of 6k plus 1 minus 1 is equal to 5 to the power of c, and 2 times 3 to the power of 6k plus 1 is equal to 7 to the power of d. We can easily see that if k is equal to 0, then we have b is equal to 2, c is equal to 1, as well as d is equal to 1. However, if k is at least 1, 5 to the power of c, which is equal to 2 times 3 to the power of 6k plus 1 minus 1, can be written as 6 times 3 to the power of 6k minus 1, or 6 times 9 to the power of 3k minus 1, is equal to negative 1 mod 9. And here we reach a contradiction similar to the one happens in the last part of case 2, which implies that there's no solutions when k is greater than or equal to 1. Therefore, the only solution in this case is 2, 2, 1, and 1. Combining all the cases, there are only 4 integer solutions for A, B, C, D, and these mark the end of our solutions. Post in the comment below if you have any thoughts on the video, and if you haven't subscribed yet, consider subscribing. These will really help us out. Anyway, see you in the next video. Thank you.